Here's a quick video, hopefully fairly quick, introducing conditional probability and independence. It's also very essential that you read the handout that I made up. That's going to have some other examples that'll help out. But I wanted to just leap off of one of the homeworks we did from the Word document, and that was this one with a small town, dogs and cats. And what it said is that out of 1,260 total households, there are 632 have dogs, and 568 who have cats, and then both was 114. And I want to ask some questions. For example, does having a dog make it more or less likely that you also have a cat? You can compare two things. Suppose I sample all the people in the town, and I look at how likely is it the person I'm talking to has a cat. It's a little under half, because 568 was a little under half of 1260. But what if I know I'm talking to a dog owner? Then it's going to be 114 out of 632. That's a lot less than half. And so having a dog actually makes it less likely that you have a cat. And that idea of saying, what if I already know some previous information? What if I actually pretend this part, the dog owners, is my entire new sample space? That's called conditional probability. And it's a really, really useful thing. Okay, so let me just write that stuff down. So let's look at the number. Let me bring this back up too, I guess. Oh, except I can't type in here and keep the focus. Okay, so let's say the number of the whole sample space was 1260. The number of dog owners was 632. The number of cat owners was, I think, 568. And the number of intersecting. I couldn't use this wonderful symbol. Oops. This very convenient symbol in Paint, because I didn't want to go to the trouble. Now let's check that. I think I had the right numbers on Paint here. Okay, 632, 568, 114. Okay. So that's all the relevant numbers. So then let's look at the probability that someone has a cat. Just straight up, that's 568 over 1260. Get a decimal for that. It's a little under half as advertised. Okay. Now what about the probability that someone has a cat, and I'm going to write it as the little vertical bar, given that they're known to have a dog? Well, you just treat the dogs as a whole sample space. So the denominator is going to be 632, and you don't put 568 up here, because if you know you have a dog, let's look at the Venn diagram, you're not going to be one of these guys. There's only 114 that you're going to count. So there's an implied intersection there. It's 114. Let me just write it out in terms of the formulas. It's the number where both things happen. You have a cat and you have a dog, divided by number who have a dog. And so that is going to be a much smaller number in this case. That's not always a smaller number. It just happens to be that in this case, having a dog makes it less likely you're going to have a cat. Okay, so it's only 18%. So that is certainly one way in problems like this, where you know all the numbers, to actually calculate the probability, what's called a conditional probability. Let me write that down. Conditional probability. We are conditioning on the event, the supposition that we actually have a dog already. Okay. So what about, how does this relate to probabilities? We'd like to get a law that didn't mention just the numbers of everything, because we don't always want to have to reduce to counting problems. We want to have a law that says, suppose somebody's calculated like the probabilities of all these things, then could we actually get this number as well? And in fact, we can. It's really quite easy. The probability of C given D is going to be, so I'm going to write that out again. Let me actually display it here so it comes a little bit bigger. So it's going to be the number in both. And then there's a very easy trick to get that to talk about probabilities. I'm just going to multiply it by the number of things in the original sample space. Because we know that the probabilities that we would have calculated already like probability of S, well, that's 1. Probability of D, probability of C intersect D. Any of those probabilities, we would have used n of S as the denominator, the 1260 is the denominator. That didn't show up directly in this calculation, so we kind of got to shoehorn it in. And so I'm just going to multiply by 1. Oops. Okay. And so that's going to be, but look at what I've got. If I pair these two together, that's the probability of C intersect D. And that's divided by, well, let's see, n of S over n of D. That's the reciprocal of n of D over n of S, and that's 1 over the probability of D. So it makes a lot of sense. What you do is you compare, you say, how likely is it that I have both a cat and a dog? Just straight up, no condition about it. How likely is it that I get in this set, but as a proportion of the probability of getting in here? And another way to say it is, probabilities behave a lot like areas. They behave exactly like areas, in fact. And so in a correctly drawn diagram, what you can do is you can say, if this diagram were drawn in a way so that the areas of the ovals and all the sets correctly represented their probabilities, which I didn't try to do here, then what you can do is you look at the area of this guy, which would correspond to its probability, but not as a proportion of the whole thing, just as a proportion of the dogs. And that's going to be, given that I'm in this smaller set, what's the probability that I get into the smaller thing? Okay. So, excuse me. There's another nice way to say that, which is often, it looks like conditional probabilities are this new weird thing that are always going to be hard, but that's absolutely not true. Often conditional probabilities are easier than the probability of two things happening. In this example, we knew the number of C intersect D, and therefore the probability of C intersect D. But a lot of the times you can actually figure out from the principles of the problem what is the probability of one thing given another. And then you can multiply that by the probability of the first thing happening, and you get the probability of two things happening. And so in fact, in that case, that's a real handy thing. So well, I'll do an example in a second. But I want to highlight the other main concept. So conditional probability. Excuse me. I know it's not ideal doing this when I'm sick, but I want to get it done. Conditional probability is one of the concepts I wanted to highlight, but independence is the other concept. We discovered in this cat and dog example that it is a lot less likely to have a cat once you know you have a dog. So knowing some information, knowing that you have a dog, affects the probability of whether you're going to have a cat. So if I think, does this person I'm talking to have a cat? If I don't know anything about them, I should say, probably 50-50 probability. If somebody gave me a bet at even odds, whether this person has a cat, it's not foolish to take that bet. It's not smart, but it's not foolish. But if they tell me, they have a dog, then I don't want to bet that that person has a cat. It's actually rather unlikely. So independence, we say two events are independent when knowing one is true affects the probability of the other one. And that's exactly a statement about does not affect, does not affect. Okay. That's the opposite of this kind of thing. Okay, and that's exactly to say that, let's continue with C and D. Let's say A and B, because A and B are not independent here. It would be when the probability of B is equal to the probability of B given A. When I don't care about that information you told me about A, it hasn't changed my mind at all. So in other words, that's because we know that's this guy with the letters changed. Probability A. Okay. Another way to say it is that probability of A times probability of B equals probability of A intersect B. This was something we were wondering about before. Is this always true? This seemed to be true, and it seemed to correspond to our fundamental counting principle. But secretly, when we use our fundamental counting principle and get multiplication, we're often actually in a situation, we're always in a situation where somehow things are independent. And otherwise, it's a little bit more subtle. So this is a more symmetric way to say independence. And it says something that's not particularly obvious. Knowing the truth of A, suppose I know that knowing whether A is true doesn't affect how likely B is. Then it's similarly true that knowing the truth of B doesn't affect how likely A is. That's interesting. This is symmetrical in A and B. This didn't seem to be symmetrical in A and B. This doesn't seem to be, but they're actually all equivalent. All these things are equivalent to each other. So here's an example of independent events. Let's say I roll, like we go back to rolling 2 dice, and E is that the first roll is a 2. I didn't need that. And F is that the second roll is a 3. So even if we had a table, I'm not going to reproduce it right here, sorry. We had a table, a 6x6 table of entries of that. And we could just calculate everything out, just like in the cats and dogs example. But suppose we hadn't done that, or suppose it's like a 1,000-sided die or something like that, or something with cards where we aren't able to write out the whole table. We know that these should be independent. The second roll shouldn't be dependent on the first. Okay, and so that's an example of an independence judgment based on the physical situation, the word problem stuff, not on some direct counting calculation. So that says that the probability of, let's say, getting both of those, the intersection of those guys, should just be, well, it's always probability of E given F times the probability of F, but because we know they're independent, that's just probability of E times probability of F. Okay. And so, and we know that each of those is a sixth. Okay, so that's looking like our fundamental counting principle in action. And it is because those events are independent and essentially identical. It doesn't really matter whether it's the first roll or the second roll. Independent, identical events give us nice things. They give us powers. This is 1/6 squared, which is 1/36. But what about non-independent? Something I know is not independent just from first principles. In this case, with the dogs and cats, I couldn't tell from first principles whether it was independent or not. I had to do the survey. I'm not really sure in this town whether once you have a dog, does it actually make you more likely to have a cat? Less likely, equally likely. It could have come either way, and the survey had to be consulted to really be sure of it. But here, like with die rolls, we should be able to do it. Well, what about a non-independent event? That would be like cards. Well, let's see. Actually, I'll do one with die rolls. It's a little different. Let's say this was, what was the event? Let's say H, I think I called it. H is the event where the first roll is greater, strictly greater than, let's just say greater than symbol, greater than the second roll. Now, does it matter? Would you like to know the first roll? Suppose I've already done the first roll, and I say, I'm willing to tell you the first roll, and then let you judge how probable H is going to be. You're going to want to know that information. If the first roll is a 6, then the second roll can be anything 1 through 5. If the first roll is a 1, then it's not going to happen. H is certain not to happen. So, for example, let's look at the independence of E. Okay, so the probability. And let's do an example of a calculation. Let's say the probability of both of these things happening. Probability of E intersect H. Remember, this is always true. H given E. So suppose I make that first roll, and I think given what the first roll is, given that the first roll is a 2, I'd like to know what's the probability that the first roll is a 2 and this condition is satisfied. The first roll is bigger than the second roll. It basically has to be 2, 1. Okay. Well, we know that the probability of getting that E was 1/6, and I'm running out of time here. The probability of H given E is once the second roll has to be a 1, and so it's only 1/6 out of 1/6. That's very, very different from the probability of E times the probability of H if you look at it from what we were doing before.